Today we're going to talk about the angle bisector theorem. And again, we're going to use a point of concurrency. Remember, the point of concurrency for the perpendicular bisector was the circumcenter. So today we'll use angle bisectors. Bisect, again, means to cut something in half. And since we're discussing angles, we're going to cut the angle in half this time instead of the line. So let's see what that looks like. So I want half of the angle, and the line is just going to go straight across from wherever half of that angle is. So this is an angle bisector. And that means that this angle and this angle are congruent. I can do that with my other angles. Cut them in half. Again, I have congruent angles. And my third angle, congruent angles. And I have a point of concurrency. Remember, a point of concurrency is where all the lines come together. It's where they agree, where they concur. So this point of concurrency is called the incenter. So what can we do with the incenter? We have the angle bisector theorem that says if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So in our last one, the perpendicular bisector, we started at the middle of the line and we had equidistant segments from the angles. This time we start at the angles and we're going to have equidistant segments from the sides. So if I go here and I drop a perpendicular, and I go here and I drop a perpendicular, and this one looks like it could possibly be on the same line. That happens sometimes. And then I go here and I drop a perpendicular. Each of these segments is congruent. The converse of the angle bisector theorem states that if a point is in the incenter of an angle and is equidistant from the sides of the angle, then it lies on the bisector of the angle. So that just means that we go from the points, these are equidistant, they meet at this point, so that means that it's on an angle bisector. The concurrency of angle bisectors of a triangle, theorem 5.7 says, the angle bisectors of triangle intersect at a point that is equidistant from the sides of the triangle. So let's see what we can do with that. Get my angle bisectors. And I'm not drawing them all the way across because I don't want them to get in the way of the perpendiculars. So we're just dropping a perpendicular line. Now, let's say that we know that this side is 12. This segment here is 12. And this is 13. What do we know about this that could help us solve for the length of the perpendicular bisectors? Well, this one we could just solve using the Pythagorean theorem, where we have a squared plus b squared equals c squared, and a is our unknown, b is equal to 12, c is equal to 13. So we would have 169. Rearranging the formula, I'm going to subtract 144, and that will give me 25. And then solving for a, because this is equal to a squared, so I have to take the square root of 25, which gives me 5, which is equal to a. So if I was actually maybe looking for this one, what would be the difference? Well, we know because these are all on the angle bisector that each of these is congruent. If I solve for the line here and I get 5, then I know that this also is going to be 5. Enjoy solving! Thanks for watching Super Math Mommy on angle bisectors. If you found this video helpful and want to learn more, you can subscribe. Click right there. Click right here to find the next video on the points of concurrency for medians and altitudes. And if you missed the previous concept, it's right there. You do want to learn more, don't you? Click there. Seriously, you're still here? Click there.